Welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this video we're going to be looking at molar relationships, but this time to do with mixed unit calculations. So where you have to compare something, for example, in mass, maybe one of the reactants in mass, and then give the answer as a volume for a gas. Or it could be to do with solutions, which could be given in volumes and concentrations. But they're all going to use the stoichiometric relationships in calculations. So in the previous video, we were looking at molar relationships for equations where both the reactant and the unknown product both have the units of mass, so grams. Here you can see we have 6.3 grams of calcium carbonate, so we know the mass of this. We're given the mass of 6.3 grams of nitric acid, so we've got the mass of this. And then it was asking us to calculate the maximum mass of the calcium nitrate. So this was what we were trying to work out. And so whilst we use the molar relationship here, which was 1 because there's 1 calcium carbonate to 2 nitric acid gives 1 mole of calcium nitrate, our grid for working this out would involve the triangle number of moles equals mass over mR. And so our calculation grid will look like this: mass, and you would fill out obviously the information that you've got. Then you'd work out the number of moles, work out which one's the limiting by doing number of moles over the mole ratio, and use the mole ratio and its relationship to the calcium nitrate that you're trying to find out in order to get the mass of the calcium nitrate produced. Okay, now if any of that didn't make sense, make sure you go and find the video on molar relationships working out excess and limiting reactants in order to understand that. Now the grid layout for this type of question is fairly straightforward because the information that we know about the calcium carbonate and the nitric acid are both solids, and also the unknown information that we're trying to achieve is also a solid. So they're all associated by the same triangle. The number of moles is mass over mR because they're the same physical state. But our next bit of this video is to look at what happens if we have different physical states and therefore different units of measurement. When we measure quantities of any substance, the universal thing that links all substances together is the idea of moles. So we say that number of moles, N, is universal as it allows us to quantify any substance regardless of its physical state. And another useful fact is that it links to the coefficient in the equation. So it allows us to work out molar relationships or molar ratio. Quantities that you deal with different substances depends on their physical state, whether they're solids, solutions, or gases. Solids are measured in masses. In order to get number of moles, we do mass divided by the molecular mass mR. Solutions are measured in volume and concentration. They are given the equation N equals V times C. Importantly, sometimes you're given concentrations in grams per decimeter cubed, and you will need to convert this into moles per decimeter cubed if you're going to try and work out the number of moles contained in a solution. Anything in this unit that you're changing is grams, which is a mass, into moles, which is N. The equation that links this together is N equals M over mR. So that leaves us with our conversion, moles being the N, grams being the mass. You divide the grams per decimeter cubed over its molecular mass of that particular substance, and then you've got the concentration now in moles per decimeter cubed. And it's at this stage that then you can input it in this equation and work out the number of moles, which allows us to compare, say, against a solid that we can work out the number of moles for. With gases, it depends whether we're at standard temperature and pressure, or if we're not at standard temperature and pressure, on what equation we use to work out number of moles. At standard temperature and pressure, we just use number of moles is the volume of the gas in decimeter cubed divided by 24 decimeters cubed. If we're not at standard temperature and pressure, we need to treat it as an ideal gas, so we use the ideal gas law. And this is pressure times volume divided by gas constant R, which is in your data sheet, times the temperature in Kelvin. And so in the exam, it's your job to identify, either given the units that you're given, so mass would be in grams, volume in decimeters cubed or centimeters cubed, and then concentration is either moles per decimeter cubed or grams per decimeter cubed, to then identify what equation you need to use in order to compare the different substances. And then your grid will change. So previously, grid for a solid would be M, Mr, and N. It's a solution, then you'd want V, C, and N. And then for a gas, it's not often that you have to use the ideal gas constant, so we're just going to use this for this particular column here. We're going to use V24N. So we're going to show how this looks in practice with some questions in a moment, but it's worth thinking about just identifying from the units or your knowledge of that particular substance which formula you're going to have to use in order to express it in number of moles, and then we can make a comparison across the physical states. So let's do our first question based on molar relationships of mixed unit type questions. If you want to have a go at this on your own, if you kind of get the concept from what we've just explained, then pause the video here and have a go. If not, we're going to just take a walkthrough for it, and then hopefully in the subsequent examples you can have a go then. So either way, I'm going to give you a bit of time to read through this question. Okay, as with any calculation question, what you want to be doing is pulling out the information that you're given and then working out what the goal is, what is the actual answer that you need to obtain. So first of all, we've been asked to work out the minimum mass of sodium hydrogen carbonate that must be heated. So we just find that in our equation, which is this one. So mass, and we put a question mark there because that's the thing we're trying to work out. And we're told the mass that we're trying to work out is that mass which produces 0.25 decimeter cubes of carbon dioxide. So we've been told a volume, and we know that from the units here, of the carbon dioxide. So V, and we put a tick there just to help us. At this stage, we start filling out our calculation grid. So I always tend to lay it out in exactly the same layout as your equation. So the mass of the question mark that we're trying to work out, we're going to put on the left-hand side of the column here. Now we've already seen a video on this, we can start populating some of the different parts. So molar ratio, obviously we've got a 2 as our coefficient in front, so our molar ratio is 2 here. Lots of students don't need this when they feel more confident. And then also we're told the volume of carbon dioxide. So we're going to fill this into this right-hand column. Again, because the coefficient is 1, we put molar ratio as 1. So you can do this all in one swoop if you feel confident. Obviously, the mass here is what we're trying to work out, so we're just going to put a question mark there. And we're given the volume here of the carbon dioxide as 0.25 decimeter cubed. So it's already in the units that we want. Now, it's worth noting that this question here, context to it is it's at room temperature, standard room temperature and pressure. So we're going to be using the equation number of moles is volume divided by 24, and that's in decimeters cubed. So we've already got the correct units. So in our column here, we're going to just put 24 in there because we're dealing with a gas. So when you're using with mixed units, the N always remains the same, but obviously if it's gas, you use volume and 24. If it's a solution, it's going to be NVC in this column. And then obviously, as sodium hydrogen carbonate, we're told it's a mass, then that is a solid, so it's going to be N equals M over MR. So it's really important to know those three triangles. Obviously, at this point, it's also worth noting if your gas is not at standard temperature and pressure, then you're using the ideal gas equation, PV equals nRT. So back to this actual calculation. So we've got 0.25 decimeter cubed. We're going to divide this by 24 as per the equation at standard temperature and pressure. And the answer to that is 0.0104. As the information we're given is just a volume of a product, we cannot use this row because it's not dealing with a reactant. So looking at our molar ratios, to go from here to this, we need to times by 2. So we're going to do exactly the same operation to our number of moles here. Then we're looking for the MR of sodium hydrogen carbonate. We need to remember that the coefficient has no effect on the MR. We're just interested in 1 unit of sodium hydrogen carbonate. So this works out to have an MR of 84.01. And then we want to work out the mass. This is our final goal. And we're dealing with a solid. So we're going to rearrange this equation here. Mass equals number of moles times MR. So our answer ends up being 1.75 grams. So we know theoretically, if we were to take 1.75 grams of sodium hydrogen carbonate, allowed it to undergo thermal decomposition, we would produce 0.25 decimeter cubed if 100% of all of this mass converted into carbon dioxide. Okay, with this exam question here, what I want you to do is pause the video in a moment. What I'd like you to do is identify what chemical substance that you know some information about, enough to work out the number of moles from, and then what the target information is that you're trying to achieve. And make sure that you are annotating the equation, because that's really going to help you then transfer it into this grid format. Just pause the video now and have a go. Okay, so if your answer was 200 centimeter cubed, then you got the full 2 marks. Now, if you didn't get this right, or you had no idea how to approach it, we're going to just do a quick walkthrough now. So we're being asked, first of all, to calculate the volume in centimeter cubed, so that's our question mark, of hydrochloric acid needed to completely react with 0.08 moles of aluminium. So if we put a question mark there, that we're trying to work out a volume of this. Now, we are given, though, concentration of the HCl, and we're told we've got 1.2 mole per decimeter cubed of the HCl. And then we're told we have 0.08 moles of aluminium. Straight away, if we've been told the moles of aluminium, we've actually been saved the first couple of steps. Because we know aluminium's a metal, therefore it's going to be a solid and so be a mass. But rather than going through the N equals M over MR, giving us the information straight away that we've got 0.08 moles of aluminium. Now at this stage, it's always worth crossing out any information that you use in the question, just to ensure that you've used all the information when you come to the end of the calculation, like we've done here. Because the equation tells us it's 2 aluminium to every 6 HCl's that need to react, our mole ratio is going to be 2 here. And because we're being asked to calculate the volume in centimeter cubed of the hydrochloric acid, on this side here, we're going to just put in the correct things for HCl. So if we just fill this out, 6 HCl, and then N, we keep those just for clarity on the same line of our grid. And then we've got concentration and volume is what we're trying to work out. The concentration we've been told is 1.2. So we're just going to put that here. Now it's really key, the units are moles per decimeter cubed. And that's going to become apparent because the answer requires it in centimeters cubed. So we're going to have to do some unit conversion. So in order to work out the volume, we need number of moles. And we can use the number of moles of aluminium that completely reacts with the HCl and the molar ratio to help us here. So we know the mole ratio based on the equation is 6. So it's 6 to 2. So let's just think about the relationship between that. Exactly the same here and get 0.24. Use the fact that for solutions, number of moles equals volume times concentration. So we rearrange that. It's number of moles divided by concentration to get volume. And that gives us 0.2 decimeters cubed. This is where you have to be really careful in the exam. If they have told you that the units have to be in centimeter cubed, you have to do some conversions. So we're going to have to take decimeter cubed in centimeters cubed. To do so, we need to times whatever decimeter cubed is by 1,000. So we do 0.2 decimeter cubed times by 1,000, we get 200 centimeter cubed, hence the answer on the answer line. Okay, so another exam question to have a go at. I'm going to get you to pause the video here and see if you can come up with an answer for this. Okay, if your answer was 1080 centimetre cubed, then you've got the full 2 marks. Don't worry if not, we're going to walk through it and see if you can work out exactly where you went wrong. So, first of all, we've been given an equation here. We've got 4 europium reacting with 3 moles of oxygen. And we've been asked to work out the actual volume of oxygen required to react with 9.12 grams of europium. It's all about translating this information into something that visibly makes sense. So volume of oxygen, you can see I put that on the equation. And then we've been told we've got 9.12 grams of europium. So we've been given a mass, so use the M there. And we know that's 9.12 grams. Let's create a grid. First of all, just isolating which substance we know information for with the tick and the substance that we're trying to work out. And then what we've got to do is just think logically. We've been given a mass for europium, so we're going to have to fill this out as mass, mR, and N. And then oxygen, we know is a gas. We've been told in this case it's room temperature and pressure, so we know we're using the N equals V over 24 decimeter cubed. We're going to fill this out in our column. Remember, keeping N on the same row. And then we've got our volume and 24 here. Good at getting in the habit. This equation always spits out an answer in decimeter cubed. You can see here the examiners trying to make sure that you understand conversions needed because they're asking you to quote an answer in centimeter cubed. So it's worth, when you're doing the grid here, just so that you don't make any mistakes in a test in that time pressured situation, of always putting dm cubed there. We just start populating it with the information that we've been given. So we've been told we've got 9.12 grams of europium, and that's the only information we've been told. Obviously trying to work out the volume of oxygen, so that's apparent, that's our goal. And so we're going to just work out number of moles, jump across using the ratio, and then work our way back up to the volume. The MR of europium is 152. A mass, or a solid, number of moles is mass over MR. So our N here is 0.06. Mole ratio, obviously coefficient here is 4, coefficient here is 3, so it's a 4 to 3 ratio. This in dividing by 4 first, timesing by 3. Dividing by 4 gives you 1 unit, and then you multiply that by 3 to get you 3 units worth. Or you can think of it as fractions, 3/4. So we're going to take our number of moles that we've worked out for europium. We're going to same operation as our mole ratio, and we're going to get the answer 0.045. Then to work out the volume in decimeters cubed, what we're going to do is use our equation, N equals V over 24, but rearrange it. Gives us the answer of 1.08 decimeter cubed. And all we need to use is our conversion of decimeter cubed into centimeter cubed, given our answer as 1.08. So what we're going to do is just times that by 1,000. Gives us 1,080, which is our answer. So hopefully you found this video useful. If you have, ensure that you like it, and then ensure that you subscribe to the channel for new videos as and when they're uploaded.